Welcome to Tech Disruptions, deep dives into the technologies reshaping industries, from AI to quantum to biotech. Let's get into it.
Okay, seriously, let's just cut to the chase. Did you see that number? 10,000 atoms? That's all it could take.
And what those 10,000 atoms could do, or rather what a quantum computer built with them could do, is shatter the foundational security of a multi-hundred-billion-dollar industry. While this specific approach would take a very long time to break Bitcoin, other recent breakthroughs suggest that breaking Bitcoin could happen in minutes.
Minutes? Wait, minutes? I thought Q-Day was decades away, like 2040, 2050, something we didn't really have to worry about yet, right? That was the consensus.
That was the consensus, until last week. This is one of those moments where the Overton window of possibility just violently shifted.
That's wild. I mean, for years, the entire cybersecurity world has been leaning on this idea that quantum computers were still science fiction when it came to actually breaking real-world encryption. We had this comfortable consensus, didn't we? This million qubit barrier, they called it.
Exactly. It was almost a comforting lie we told ourselves. The common wisdom was that quantum computers, while powerful, were inherently noisy. They're super sensitive to environmental interference, which means errors are rampant. To do something complex like Shor's algorithm, the math that breaks encryption, you need these perfect, stable, logical qubits.
And those logical qubits, as I understand it, are essentially virtual constructs, right? Made up of many physical, flawed qubits acting as backups.
Precisely, and the ratio was brutal. Using the industry-standard surface codes on superconducting chips, you needed roughly 1,000 physical qubits to make just one stable logical qubit. Now, to break something like elliptic curve cryptography, you need a couple of thousand logical qubits. So, do the math. 1,000 times 2,000, you're looking at 10 to 21 million physical qubits. With today's best processors only in the hundreds, Q-Day felt safely decades away.
So we were all tucked into bed dreaming of a quantum-safe future, and then Caltech comes along with Oratomic and throws a wrench in the whole thing. What did their paper say?
Their paper, titled Shor's Algorithm is Possible with as Few as 10,000 Reconfigurable Atomic Qubits, fundamentally rewrote that equation. The researchers, led by Madeleine Kane, Chen Xu, Manuel Endres, and the legendary John Preskill, the guy who coined quantum supremacy, shattered that 1,000 to 1 ratio. How? What did they do to shrink it so dramatically? They utilized new high-rate quantum error-correcting codes, specifically something called lifted product codes. This allowed them to achieve encoding rates of roughly 30%. What that means in practical terms is that instead of 1,000 physical qubits for one logical one, the ratio drops to approximately 5 physical qubits for one logical qubit.
5 to 1? From 1,000 to 1? That's not just an improvement, that's a paradigm shift. So applying that new math, where does that put the new target for breaking encryption?
It plummets from those millions of qubits down to between 10,000 and 26,000 physical qubits. It's an order of magnitude, several orders of magnitude, reduction in scale. And to underscore the gravity, John Preskill himself, who's been at this longer than some of his co-authors have been alive, summed it up perfectly. Now, at last, we're getting close.
Getting close? Understated much. That's incredible. But how do you even achieve that 5 to 1 ratio? Are they just building better superconducting chips, or is it a completely different approach to the hardware?
It's a completely different approach, and this is where it gets really interesting. For years, tech giants like Google and IBM have focused on superconducting qubits. Think of these as artificial atoms, essentially printed onto silicon chips. They're locked in place. The problem is, because they can't move, they can only talk to their immediate neighbors. That limitation forces them into those highly inefficient error correction codes we just talked about.
So, like a very rigid, fixed communication network.
Exactly. The Caltech/Oratomic team, however, uses neutral atom quantum computing. Instead of these artificial, fixed atoms, they use actual, identical atoms, like rubidium or strontium, suspended in a vacuum. It's a fundamentally different substrate.
Actual atoms floating in space? That sounds like something straight out of a sci-fi movie. How do you even manipulate those?
That's where the sci-fi element truly comes in. They use what are called optical tweezers. Imagine highly focused laser beams that act like microscopic tractor beams. During a computation, these lasers literally pick up individual atoms and shuttle them across the grid to interact with other atoms, even on the opposite side of the processor.
So it's not just static connections. The qubits themselves are physically moving to where they need to be. It's like a massive game of musical chairs, but at the speed of light with atoms.
That's a fantastic analogy, and it allows for non-local connectivity and massive parallel operation. Because an atom can physically move to back up a failing atom anywhere on the board, the error correction becomes exponentially more efficient. It's like having a perfectly flexible workforce that can instantly reconfigure itself to solve any problem.
Okay, so this isn't just theoretical whiteboard math, is it? Is there any real-world proof that this is even possible?
Not theoretical at all. The margin between theory and reality here is actually uncomfortably thin. Back in September 2025, Manuel Endres, one of the senior authors on this new paper, and his Caltech colleagues published a paper in Nature where they demonstrated something incredible. They had successfully trapped 6,100 neutral atoms in a laser grid.
6,100 atoms, and the target is 10,000. So we're talking about an engineering cycle, not some distant theoretical future.
Precisely. The gap between what they've already demonstrated and the 10,000 atom threshold proposed in this new paper is a single engineering cycle. It's not a conceptual leap, it's a scaling challenge.
So Caltech is attacking the hardware side, shrinking the number of physical qubits needed. But the source material also mentions Google entering the fray, and they attacked the algorithm side. And this happened on the exact same day?
The exact same day. It's almost too coincidental to be mere chance. While Caltech dropped their hardware bombshell, Google Quantum AI published a 57-page white paper titled Securing Elliptic Curve Cryptocurrencies Against Quantum Vulnerabilities. This paper carries massive institutional weight, co-authored by Google's top minds like Ryan Babush and Hartmut Neven, alongside Ethereum Foundation researcher Justin Drake and Stanford cryptographer Dan Boneh.
So a heavyweight lineup. What did they find?
Google focused specifically on the elliptic curve discrete logarithm problem, or ECDLP-256. This is the specific mathematical lock that secures Bitcoin, Ethereum, and a huge chunk of the broader web. They discovered clever ways to streamline the quantum steps required to run Shor's algorithm, including smarter ways to reuse qubits during the key calculation.
Streamlining the process, essentially making it more efficient?
More efficient, more compact. The result? They proved that cracking this specific cryptography requires roughly 1,200 to 1,450 logical qubits. And translated to Google superconducting hardware, this requires fewer than 500,000 physical qubits. That's a 20-fold reduction from the previous estimates of 10 million physical qubits.
So Caltech brought it down to tens of thousands, and Google brought it down to hundreds of thousands. Both are massive reductions. But you mentioned something earlier about minutes. Which one delivers that kind of speed?
That's the critical difference. While the neutral atom approach from Caltech requires fewer total physical qubits, potentially as low as 10,000, moving physical atoms with lasers is, relatively speaking, slow. Google superconducting chips, however, are lightning fast. The Google paper estimates that a 500,000 qubit superconducting machine could crack a Bitcoin private key in just 9 to 12 minutes.
9 to 12 minutes. Let that sink in for a second. We went from decades away to under 10,000 atoms and 9 minutes. That's truly astounding. And Google actually figured out the exact quantum circuits needed for this attack, but they refused to publish them?
This is where the story gets incredibly cyberpunk. The researchers confirmed they did figure out the precise quantum circuits, but they recognized that publishing that blueprint would literally hand a multi-billion-dollar heist plan to hostile nation-states or sophisticated criminal organizations. So, adhering to responsible disclosure norms, they published a zero-knowledge proof.
A zero-knowledge proof. For those not deep into crypto, what does that mean in this context?
It's a cryptographic guarantee. It allows the global math community to verify their research estimates. These claims of needing 500,000 qubits or a 9-minute hack time are 100% accurate without ever seeing the underlying code itself. It's like proving you know a secret without revealing the secret. It's a genius move to confirm the threat without providing the weapon.
Okay, so we've established the how and the when. Now let's follow the money. Why did Google focus its research on cryptocurrencies rather than, say, banking systems or nuclear codes, which seem like bigger targets?
Because blockchains, particularly their cryptography, are uniquely structurally vulnerable to quantum attacks in a way that traditional finance isn't.
Can you explain that difference?
Absolutely. Traditional finance, for the most part, still relies on RSA encryption, which uses massive key sizes that will take quantum computers longer to crack. Blockchains, on the other hand, use elliptic curve cryptography, or ECC. ECC uses much smaller keys, which makes it significantly easier for a quantum computer to break. So, a quantum computer will be able to crack ECC years before it can crack RSA.
And the consequences are different too, right? If a bank gets hacked, there are mechanisms to reverse transactions.
Exactly. If a bank gets hacked, transactions can often be reversed or funds recovered. If a blockchain gets hacked, the theft is immutable and irreversible. Once it's gone, it's gone. That's why Google focused here, because of their unique vulnerability to quantum attacks.
So what's immediately at risk? Are we talking about current transactions or something else?
The most immediate glaring threat lies in what are called exposed public keys in dormant wallets. Modern Bitcoin wallets hash the public key, adding a layer of protection. But in the early Wild West days of Bitcoin, transactions often used pay-to-public key, or P2PK scripts. These literally broadcast the public key directly to the blockchain.
So if you used one of those old wallets, your public key is just out there, waiting?
Precisely. And according to the data, there are between 1.7 million and 2.3 million Bitcoins sitting in these highly vulnerable dormant addresses. This includes the legendary stash mined by Satoshi Nakamoto himself.
2 million Bitcoin. At current market prices, that's hundreds of billions of dollars just sitting there, waiting for the first person to turn on a cryptographically relevant quantum computer. That's an insane bounty.
It is, and it's not just Bitcoin. Across the broader ecosystem, including Ethereum and stablecoins, over $600 billion is directly exposed to this specific vulnerability. It's a massive visible target.
Okay, but that's dormant wallets. What about new transactions? If I send Bitcoin today, am I safe?
Not necessarily. This is where the live attack nightmare comes in. Remember Google's timeline? 9 minutes to crack a private key? The Bitcoin network takes, on average, 10 minutes to confirm a block.
Oh no, I see where this is going.
A quantum attacker could spot your transaction in the public mempool, that's the holding area for unconfirmed transactions, crack your private key in 9 minutes, and then broadcast a forged transaction with a higher miner fee. That forged transaction would then be picked up by miners and confirmed before your original transaction even clears, essentially stealing your funds in transit.
That's terrifying. So you initiate a transaction, and before it's even confirmed, a quantum computer could swipe it? What's the probability of that happening?
Researchers estimate a 41% probability of theft during this live broadcast window. It's not a certainty, but it's a very significant risk. And this threat is very real to the people working on this. Justin Drake of the Ethereum Foundation, who co-authored that Google paper, didn't mince words. He posted to X that his confidence in Q-Day by 2032 has shot up significantly. Google itself has even set an internal 2029 deadline to complete its post-quantum cryptography migration.
2029? That's not far off at all. But you know us, we're tech disruptions. We have to throw a bit of a reality check into this. There's always some hype wrapped around these big announcements. What's the catch? What are we missing?
You're right to be skeptical, and there are a few things to consider. Let's start with the timing. On March 31, 2026, the exact same day that Caltech paper dropped, a 14-person startup named Ortomic officially launched. The CEO is Dolev Bluestein, a Harvard PhD, and the CTO is Robert Huang, who's taking a leave of absence from his Caltech faculty position to build this company.
So, a paper dramatically accelerating the timeline for quantum utility just happens to be published on the exact day the authors launch a venture-backed startup to build that exact machine? That's convenient.
It's certainly a strong signal of commercial incentive. You have to ask, what are the financial motivations behind publishing timeline-accelerating research while simultaneously pitching venture capitalists to fund a mission to build a utility-scale quantum computer by the end of the decade? It certainly creates a narrative.
Agreed. And what about the fine print on the math itself? Is that 10,000 qubit claim completely solid?
It is, but with a significant caveat that a skeptical quantum researcher named Manat Sharma pointed out. Yes, 10,000 physical qubits can theoretically run Shor's algorithm, but because neutral atoms move relatively slowly, running that algorithm on just 10,000 qubits would take approximately 1,000 days of continuous, flawless computation.
1,000 days? That's almost 3 years. Maintaining a fault-tolerant quantum state for nearly 3 years sounds like pure science fiction at this point.
It absolutely is. So while the 10,000 number is accurate for theoretical minimum, to execute the attack in a more realistic time frame, say weeks or months, Ortomic's own preliminary estimates suggest you would actually need closer to 26,000 physical qubits. That's still a massive improvement from millions, but it puts it back in perspective.
And there's a difference between just having atoms and actually doing something useful with them, right? Like trapping 6,100 atoms versus performing complex computations.
Exactly. Manuel Endres has trapped 6,100 atoms, which is a monumental achievement. But high-fidelity entangling operations, the actual logic gates that perform computations, have only been demonstrated on regions of a few hundred qubits. Scaling that pristine, low-error control across tens of thousands of atoms is a monumental engineering challenge that we haven't seen overcome yet. It's like having all the bricks for a skyscraper, but only knowing how to lay the foundation for a small shed.
So it's not a done deal, but it's not a fantasy either. It's a very clear path forward.
It is, despite the healthy skepticism regarding Oratomic's commercial launch and the engineering hurdles of sustained error correction, the fundamental reality of the tech landscape has changed.
So let's synthesize this for our listeners. What are the key takeaways from all this?
First, the goalposts have moved dramatically. The industry can no longer hide behind the million-qubit barrier. Whether it's 10,000 atoms or 500,000 superconducting circuits, the hardware requirements for cryptographically relevant quantum computing have shrunk by orders of magnitude. Q-Day is no longer a distant theoretical threat.
And second, that crypto ticking clock?
Absolutely. There's a $600 billion bounty sitting in plain sight, protected by math that Google has now proven is 20 times easier to crack than previously believed. The financial incentive is enormous, and the vulnerability is known.
Which leads to our third insight, the migration mandate.
Yes, blockchains are uniquely vulnerable, and migrating a decentralized network like Bitcoin to post-quantum cryptography, or PQC, requires immense community consensus. That's a process that historically takes years. With Q-Day estimates pulling forward to 2029-2032, the crypto industry no longer has the luxury of time to debate. They need to start migrating, and fast.
So here's a thought for our audience. If you knew the lock on your bank vault was going to melt in 2030, when would you start moving your money? Because for those 1.7 million dormant Bitcoin, the countdown has officially started.
That's all for this episode of Tech Disruptions. Join us next time as we keep exploring the technologies reshaping our world. Thanks for listening. We'll see you next time.
Stay curious out there.